So we have talked last time about collisions and collision types and what kind of equations we use, the conservation rules that we should use in order to study collisions. Namely, we said a collision is an interaction between two objects, and we distinguished between three types. One, a completely elastic collision, where all of the energy transferred is simply kinetic. This is the elastic collision. One car collides with the other, but simply pushes it forward. No deformation in either car. In this case, I will say that the total energy transfer is just kinetic, and thus the kinetic energy before the collision is equal to the kinetic energy after the collision for both objects, our system of interacting objects. And for any collision where there are no external forces, and basically in this chapter we are going to consider only cases where there are no external forces. So in these cases, we're going to consider that the linear momentum is conserved, and this is my second equation. I want you to notice how the kinetic energy equation is a scalar equation, and this is a vector equation. So if there are signs, if there is a speed that is to the right or to the left, I have to acknowledge that and place negative signs. Whereas in the kinetic energy, because it's a scalar equation, then I don't have to put any pluses or minuses. Our second kind of collision is a partially inelastic collision. Here, some energy is lost for the deformation. So I cannot say that the kinetic energy is conserved because some of the kinetic energy of the first car here, namely, is going to be transferred to deformation and vibrational energies due to the change in the shape at the front. So here, some of that kinetic energy is transferred or converted to other types of energy, such as heat and work, to permanently deform the object. Here I will say only the linear momentum is conserved. And finally, in the completely inelastic collision, the two objects stick together into one object. Here, I will write the linear momentum to be conserved and becoming one linear momentum after the collision. So today I'm going to be solving some examples on that. Namely, I want you to check this easy example on a completely inelastic collision. An arrow collides with a pendulum and lifts it a little bit. So this is a very important question. Since the two objects stick together, then this is a completely inelastic collision. And in a completely inelastic collision, the conservation of linear momentum is used. Here, I cannot say K1 plus K2 equals K final. No, since some energy is lost in the deformation. Namely, we have the deformation where the two objects become one. So here something is definitely changing in both objects. So I'll have only the linear momentum to study, and I'll take it from there. I'm gonna check my formulas for the linear momentum. So what do we have in the question? We have a ballistic pendulum used to measure the speeds of bullets before electronic timing devices were developed. So this device, the ballistic pendulum, we use it to measure the speeds of bullets. How do we do that? So we have a large block of wood of mass 5.4 kilograms. Here it is. Hanging from two long cords, a bullet of mass 9.5 grams is fired into the block, coming quickly to rest. The block plus bullet then swing upward, their center of mass rising a vertical distance h equals 6.3 centimeters here, before the pendulum comes momentarily to rest at the end of its arc. What is the speed of the bullet just prior to the collision? So what we want is the speed here. This is basically V1 initial, which shows up in this equation. I have M1, V1 initial, plus M2, V2 initial, equals M plus M1 plus M2 times V. So what we want is this. I'll rearrange for the initial speed of the bullet. I'll get m1 plus m2 v minus m2 v2 initial over m1. Now, the very nice thing here is that the block initially was at rest. So the bullet is fired towards this stationary block and it wasn't moving. Then the system of both bullet and block lift upwards. I can also show you a simulation, by the way. This is a ballistic pendulum in action. So we fire an arrow, it hits the block, and it lifts up. You can see the close-up here. So the arrow hits the block and then lifts it upwards. So the block initially was at rest. The arrow is fired towards it, so the arrow has a non-zero speed. And then both move together. Okay, let's take a look at our equation. Then I'm gonna set V2 initial to be 0. I end up with this formula. M1 is the mass of the block. Well, no, I'm taking object 1 to be the bullet. So M1 is the mass of the bullet, which is 9.5 grams. I'll convert that to kilograms. M2 is the mass of the block, which is 5.4 kilograms. The values make sense. You will need a very large block to stop the very fast bullet. So we use a larger object. The bullet itself is usually light in weight. So here it has a mass of 9 grams, basically, which I converted to kilograms. And here I have M1 in the denominator, and this is where a problem shows up. I have here V, which is the speed of the block bullet system after collision. This speed, I don't have it. I wasn't told what the system speed is after the collision. Rather, I'm actually told something different. I'm told that the block plus bullet swing upward and their center of mass rises a vertical distance of 6.3 centimeters. So I'm told about the height that the system lifts due to this acquired speed. So what are we talking about here? Let's go back to our um, demonstration. You can see when the arrow hits the block, then they have a speed, but this is a pendulum. A pendulum would always just lift upward. It will not move translationally. It will move across an arc. It will not move linearly. And as it moves through this arc, it reaches a certain maximum height. Why? Because of its initial speed and it's lifting upwards, then its kinetic energy converts to potential energy. And at maximum height, I know that U is max and K is 0. At maximum height, the speed becomes 0. I'm gonna make use of that. And this is what we saw in our study of chapter 8 of energy. So I'm gonna be applying this here, hoping that I can find from the potential energy, the kinetic energy, and thus the speed. Because if I have the height, then I can use that to find the potential energy of the system. So I'm gonna study conservation of energy, and I will say E right after collision equals the energy at maximum height. Now, right after collision, I have only kinetic energy. I'll take my zero reference to be here just after the collision. The system was here. This is my zero height. So I don't have any potential energy. I only have the kinetic energy acquired from this speed that is obtained from the collision. At the maximum height, it's the other way around. I don't have a kinetic energy. I only have a potential energy. This is after collision equals U max at the maximum height. Now, after the collision, K is none other but half into M1 plus M2 V, where V is the speed after collision. And Umax is the maximum potential energy, which is M1 plus M2 G H. H is the maximum height. Now I have the maximum height. It's 6.3 centimeters. The masses here actually cancel out, which is great. It will make the equation look way easier. This is V squared. So I'll get radical 2GH, and here I'll have 2 times 9.8 times H, which is 6.3 times 10 power minus 2. I'm going to calculate this. I'll get 1.1 meters per second. I'm not going to stop here. I need to calculate V1 initial by plugging V to be 1.1 now. So I'm going to get I got 630 meters per second, which is quite huge, and that makes sense. Bullets are usually very fast. Let's just double check my answer. Yeah, this is correct. 630 meters per second. This is the speed of the bullet right before the collision. So we talked about collisions, and I told you that the linear momentum conservation equation is actually a vector equation. So if any speed is like negative or to the left, then I'll place a minus sign in front of the corresponding linear momentum. Whereas the kinetic energy conservation is considered a scalar equation. So I will not put any negative signs in it. I will always add the kinetic energy as it is, as linear magnitude values, and I will not put negative signs. So here I'm going to be focusing a bit on how we can project. So I want you to see this arrangement where I have a ball, it's moving to the right, and then it hits a second ball, which is stationary, and then both move at different directions. So here, because the velocities are moving in different directions after the collision, they will have x and y components. So if you look at our equations, the conservation of linear momentum, which is a vectorial equation, I'm going to have to project it along x and y directions. Namely, this is mass 1, and it will collide with mass 2. After the collision, m1 gets deflected downwards, whereas m2 moves upwards. So their velocities are oblique. I cannot add them linearly in the conservation law. I will have to account for x and y directions. So I will project along x. If you project along x before the collision, m1 was already along x. So I'll put v1 initial as it is in the equation. m2 is stationary, so it will have no speed. After the collision, v1 is deflected downwards, so I'll put m1 v1 final times cosine theta 1. I'll check the angle that V1 makes with the x-axis. I'll make a similar study for V2. V2 makes an angle theta 2 with the x-axis, so its x component will be V2 final cosine theta 2. This is my conservation law along the x-axis. I'll also study the y components. Now M1 has horizontal speed, so it will not have a y component, so I'll put 0 before the collision. After the collision, V1 final has a y component, which is negative V1 final times sine theta. So I'll just plug that. And you can do the same thing for V2. After the collision, V2 will have a y component, which is positive V2 final times sine theta 1, theta 2, sorry. So we get this equation along the y direction. And If the collision is elastic, I can also study conservation of kinetic energy. I'll put K1 initial plus K2 initial equals K1 final plus K2 final. But here I will not project because this is a scalar equation. Now K2 is 0 because M2 was at rest, so I'll just cancel that out and I obtain this equation. And we can basically solve for whatever speed we're looking for. As you can notice, these are three equations. So if I have three unknowns, then I can totally solve for these three unknowns using these three equations. So in this question, we're basically colliding an alpha particle, which is basically a helium nucleus, by the way, with an oxygen nucleus. The alpha particle is scattered after the collision at angle θ1 equals 64, and oxygen recoils with a speed 1.2 times 10 power 5 meters per second at an angle θ2 equals 51 degrees. In atomic mass units, the mass of the alpha particle is 4, the mass of the oxygen is 16. What are the final and initial speeds of the alpha particle? So I'm gonna just write things down. So one thing I know is the alpha particle was targeted towards the oxygen molecule, oxygen nucleus actually, and then it's scattered. So the alpha particle moves at an angle 64 after the collision, whereas our oxygen atom will move at an angle 51 with a recoil, so it's opposite. So this is my figure, which is very helpful. This is V1 initial, this is V1 final, and this is V2 final. So I'm gonna study conservation of linear momentum, and I wasn't told that this is elastic, so I really cannot study conservation of the energy. So if I study linear momentum, I'll have P1 initial equal P1 final plus P2 final. That's what I have. Notice how the oxygen atom was initially at rest, so it will not, I did not include it in the initial linear momentum. Now let's take a look at what we have. I have M1 V1 initial equals M1 V1 final plus M2 V2 final. These all are vectors. I'm gonna project along X. I have M1 V1 initial equals M1 V1 final cosine 64, and I have plus M2 V2 final cosine 51. This is the equation along the x-axis. Along y, I have 0 equals M1 V1 final sine 64 minus M2 V2 final sine 51. Notice how the oxygen nucleus recoils, so it will have negative y component for its velocity. If you can't see it, I recommend that you draw x and y axes. So these are my speeds, V1 final making an angle 64 and V2 final making an angle 51. So if you draw the x and y axes, you can clearly see the angles. This is the x-axis, this is the y-axis. So we'll find x and y components, and you can see how if you project V2 final on the y-axis, it's negative. So I'll put a minus sign. Okay. Again, what was our question? What were we trying to find? We wanted the final and initial speeds of the alpha particle. So what I want is
V1 initial and V1 final. These show up here in these equations, which is perfect because my second equation has only V1 final as an unknown. I can find V1 final. It will be M2 V2 final sine 51 over M1 sine 64. I'm told that the oxygen nucleus recoils with a speed 1.2 times 10 power 5. So I actually have these, I have this speed. That's good. I'm gonna just substitute. M2 is the mass of the oxygen nucleus, 16 units. Here I have 4 units. V2 final is 1.2 times 10 power 5. And here I have sine 51. I can find the speed of the helium nucleus after the collision. This will be 4.15 times 10 power 5 meters per second. This is part A. So what remains is part B, where I want the initial speed of the alpha particle. And here I'm going to use my first equation, which is along the x-axis, where I wrote, let's copy that. I wrote M1 V1 initial equals M2 V1 final plus M2 V2 final with projections in the appropriate angles. So I'll just paste this here. And we're just gonna, the rest is just substitution really. So I'm just gonna substitute. Okay, this is my equation. What we want is V1 initial, the initial speed of our helium nucleus. So I'll put V1 initial to be equal to M1 V1 final cosine 64 plus M2 V2 final cosine 51 over M1. M1 was 4, V1 final, we just found it, it was 4.15 times 10 power 5. I have cosine 64 here plus 16 plus times V2 final was 1.2 times 10 power 5. And here I have cosine 51, and here I'll divide by M1, which is 4. And I can find V1 initial. If you calculate this, you'll get 4.84 times 10 power 5 meters per second. Notice how the initial speed of the alpha particle must be larger than the final speed. It is a bit larger, you know? It's a lot larger. This is times 10 power 5. So that makes sense because the oxygen was at rest. So the speed of the alpha particle will be distributed on both the oxygen and the alpha particle after the collision. Does this make sense? All right.